So here's the first problem we're going to take a look at. I have a 16-foot long beam here, all right, and here I have distributed loads upon it, all right. So what is a distributed load? Okay, we actually had one a little earlier in the semester where we were looking at center of mass, and I put a box on a cantilevered beam. Okay, straighten that out here. And so the weight, while we can consider the weight, there's actually distributed load in the beam. It effectively is all the weight right at the mass center, but there's a distributed load happening. So we have the same idea here. Picture I have a 4-foot long box that exerts 200 foot per pound on this beam. All right. So it's uniform. So picture a uniform box, as it were, 200 pounds per foot. So that would exert 800 pounds. And so right below here, you'll see I have the free body diagram. All right. So the center of mass of this distributed load is right here in the center. So here's 800 pounds, 2 feet, 2 feet. So we have a pin joint that'll produce set a force up. It could also exert a force in the X, but note there are no X forces on this. So therefore, there is no need for an FAX. The next 8 feet has a 300 pound per foot load. So picture a great big box that exerts 300 pounds over every foot uniformly. 300 times 8, that's 2,400 pounds. So we'll just put that effectively in the center of mass right here, imagining that we had a box there. So 4 feet, 4 feet. And here we have expansion joints. So this only can exert a force in the Y. And then once again, we have another box exerting 200 pounds per foot here. All right, so that distributed load can be broken down as 800 pounds right there. And so we have all our spacings. So we're going to start building up our process for solving these problems. And so the first step in these problems will always be step one, do a free body diagram. And then step two, figure out what the supports are doing. All right, so we have this right here. If I sum the moments a day, I generally always sum the moments to the left, and I kind of tend to work problems from left to right. That's my way. You could sum the moments at B, nothing wrong with that. If you do sum the moments a day, you have the 800 2 feet away going counterclockwise positive, then this would be 2,400 times 4 negative. FB going counterclockwise times 8 minus, here we have 800 pounds 10 feet out. Solve, you get FBY. FBY, the support here is doing 2,000. So then if you add these up, you have 24, 32, 4,000. It says AY is also 2,000. Dare I say, once you compute this, this is obvious, okay? Everything is symmetrical. So in fact, what you could do is just look at both, add up the top, 4,000, because these are symmetrical. You could have said 2,000 and 2,000, and you'd been on very sound ground. All right, but that's the process. All right, so for this problem, I want to find the shear, the bending moment, the normal, or axial force at C and D. All right, C is dead in the center. All right, easy to get our head around that. And D, now you see there's a separation here, but that's just so you can see it. I want you to envision that D is imperceptibly to the right of here. So the distance from here to there is 0.00001 meters, okay, or feet. Very, very small. Okay, I drew it separate just so you could see it, but the idea is it's right at the edge. All right. So after you get the supports, I'm going to go after D first. So we're going to find out what is the shear bending moment and the axial load in the center. Okay, so let's comment on this. What forces are there in the X here? There aren't any. So the axial force, 0. We're done with it. All right. So now we're going to look at everything else. So this is, since D is imperceptibly far away from B, This is from D to the end, it's 4 feet. So what happens is when if I want to look at D, I basically come in, chop off the beam, and replace everything that's thrown away with a force and a moment, the shear and bending moment, just to the side of B. So as a result, because I'm just to the side, I'm missing the support force that's there. All right. So when I do that, so here's a free body diagram. I just have this piece here. So that's 200 times 4, 800 pounds, 2 feet, 2 feet. And we're taking all the beam away. And here's the shear it provides to support it. There's the bending moment. Now, here's what I want you to know. Whenever you draw these free body diagrams, let me move this up a tab. All right. When you draw these free body diagrams, note, I drew the shear up. Why? Because that would take this thing clockwise. We are working towards where we're going to do plots of these things. All right. We're going to plot shear. We're going to plot bending moment. All right. So when you go to do these problems, always set these up as if so that when you solve them, it is aligned with the coordinate system for shear and bending moment. So positive shear would try to take this clockwise. Positive bending moment tries to pinch the top. So I drew them accordingly. And then if I get a negative, I'll go, oh, if this works out negative, oh, I'm pinching the bottom. That's fine. But that way I'll have the sign I need for my plot. All right, so these were drawn in positive based on the sign convention. So if I look at this isn't worth a lot of time in my mind. 800 down, so indeed VD does go up. All right, so there's 800 pounds. All right, absolutely not exciting. By the same token, all right, if I look at this here, let's just write what we have. So if I sum the moments, let me sum the moments right here. I have 800 times 2, so I've got minus 1600. All right. And then this is oriented currently clockwise, minus m at D, and set that equal to 0. By taking the moments here, VD drops out. Solve for that. Bring MD to the other side, and I'll just put an arrow there. MD equals minus 1600 foot-pounds. All right, got a negative. So what that says is this isn't pinching the top, it has to pinch the bottom. Well, that makes sense. If this is trying to go clockwise, I need this to go counterclockwise to balance it. And so we don't have this thing twisting off like that. So this is 800. We have 800 here. We have minus 1600 there. Okay? Now we're going to move on and we're going to take a look at point C here. So let's set this up. So here's our beam. We want to look at what's happening in the center here. So here's the free body diagram for that. I'm going to chop it right here at C. I'm throwing this half away. It's gone. I replace them with a shear, trying to go clockwise, with a bending moment, trying to pinch the top. Okay. Now, for the part of the beam that's left, I have 300 pounds per foot over 4 feet. That would put, for what is left of the distributed load, I have 1,200 pounds and I put it at its center of mass. Okay, right dead in the center here, 1,200 pounds. And this 800 is still there, it's just in the same spot. All right, and now I have this support, which I know is 2,000, so I put that in. Okay, so next step, Very simply. If you sum the forces, 2,000 up, 2,000 down, shear is 0. All right. Last step we need to do is figure out what is the moment right here. Okay, so I typically take, wherever I cut the beam is where I take the moment because that takes the shear out of the equation. We'll make this a little bigger for you. All right, so taking the moments here, I have MC, which is currently drawn clockwise. So here's MC. All right, this is going clockwise, minus 1,200 times 2. Now we have 800, that's 6 out, minus 800 times 6, plus 2,000 times 4. All right, solving for this, we get MC is 800 pound-foot, or foot-pound. So I got a positive. So this is indeed, so in net, there's a torque going this way, and this torque counteract, this torque, oops, said that wrong. There's a torque going right here. There's a torque going that way, and this one is then counteracting it to keep it in place. So we've got shear at C is 0, bending moments 800 foot-pounds. That'll end this video. We'll do another problem here in a moment.